In a system design interview, the biggest mistake is jumping straight to the solution. First, we must clarify the scope. Let's say the interviewer asks us to design an ad-click aggregator. This sounds simple, but the devil is in the details. I start by asking, do we need real-time results, or is a daily batch job enough? The interviewer specifies real-time. Next, I ask about accuracy. For billing advertisers, we usually need exact counting, but for a live dashboard, a small margin of error might be acceptable. Then, the big question, scale. They tell us we need to handle 1 million events per second. This immediately tells me a standard database won't work. Finally, who is consuming this data? It's for an advertiser dashboard to see top-performing ads. So, we have our functional requirements, real-time aggregation. And our non-functional constraints, massive throughput and low latency. Let's do some back-of-the-envelope math. If we have 100 million daily active users, and each clicks about 5 times a day, that gives us 500 million clicks per day. To convert this to queries per second, we divide by the seconds in a day, roughly 100,000. That gives us an average of 5,000 requests per second. But traffic isn't flat. At peak hours, we usually multiply by 3. That's 15,000 writes per second. Now look at storage. Even at 0.5 kilobytes per click, 500 million clicks generates 250 gigabytes of data every single day. That's nearly 100 terabytes a year. A single MySQL instance would choke on this write volume and run out of space in months. We need a distributed approach. Here is the high-level architecture. We place a load balancer at the edge to distribute traffic, but we don't send it straight to the database. Instead, we use a message queue, like Apache Kafka. This acts as a buffer, decoupling our ingestion from our processing. Next, we have the aggregator service. This is a stream processor, like Flink or a custom consumer, that reads the raw events. It summarizes the data in memory and writes the final counts to an OLAP database. But the interviewer will ask, what happens if your aggregator crashes? If this server dies, we lose all the clicks currently in memory. That's money lost. To fix this, we use offset commits or checkpointing. We periodically save our position in the stream, so if we crash, a new worker can resume exactly where we left off. A single queue is a bottleneck. If we have millions of clicks, one consumer can't process them fast enough. The lag creates a backlog. The solution is partitioning. We split the Kafka topic into multiple shards, say, partition 0, 1, and 2. But we can't just distribute them randomly. We need to aggregate clicks for the same ad together. We use a consistent hashing strategy, hash of the ad ID modulo the number of partitions. This ensures that every click for ad 101 always lands in the same partition. This allows us to scale horizontally. We can have different servers processing different ads in parallel, without ever needing to lock a shared database. Now for the database schema. Since we are dealing with massive write volume, a standard SQL table might lock up. We choose a NoSQL store like Cassandra or ScyllaDB. These are optimized for fast writes. We don't store individual user clicks here. We only store the aggregates. For example, for ad 101 at 10 o'clock a.m., we simply record 50 clicks. At 10:01, we record the next batch. The magic lies in the primary key. We use a composite key, ad_ID is the partition key, and minute_mark is the clustering key. This ensures all data for a specific ad is stored physically together on disk, making the query show me ad 101's history incredibly fast. In distributed systems, networks fail. If a client sends a click and doesn't get an ACK, it retries. Now we have 2 events for the same click. If we count both, we overcharge the advertiser. That's unacceptable. To solve this, we implement an idempotency key. We can use a lightweight cache like Redis or a Bloom filter. Before processing, we check if we've seen this event ID recently. If we have, we drop the duplicate. If it's new, we process it and mark the ID as seen. This guarantees exactly once processing semantics. Let's look at consumer groups. We have 3 workers, each responsible for one partition. Suddenly, worker 1 suffers a hardware failure and stops sending heartbeats. The Kafka broker detects the timeout and triggers a rebalance. Partition 1 is automatically reassigned to worker 2. Worker 2 now handles double the load temporarily. The system heals itself. Once a replacement for worker 1 comes online, the group rebalances again to share the load evenly. Finally, how do we serve this to the dashboard? We use a hybrid approach. We write real-time counts to a cache like Redis, and historical data to a disk-based database like Cassandra. When the user asks for live clicks, we hit the cache. It's incredibly fast but volatile. When they ask for last month's trends, we query the columnar database, which is optimized for reading massive ranges of time series data. This separation ensures that heavy historical queries don't slow down our real-time ingestion pipeline. So, bringing it all together, here is our complete ad-click aggregator. Data originates from millions of client devices, hitting our load balancer, which immediately offloads them into our Kafka stream. This buffer ensures we never lose data during traffic spikes. Our partitioned workers consume these events in parallel. They deduplicate using Redis and aggregate counts in tumbling windows. Once a window closes, the final count is written to our persistent storage layer, Cassandra for long-term history, and Redis for instant access. Finally, the advertiser dashboard queries these views to display real-time analytics with sub-second latency. And that is how you design a scalable, fault-tolerant system capable of handling millions of events per second.